Hello, my name is Malak,
And you're Apache.
and our device is a passive stretching device. Our aim is to improve the range of motion of our client's hand that is suffering from spasticity by developing a mechanism that passively stretches his hand and wrist to supplement the absence of better options.
And this is a collaboration work with the University of Detroit University. Our advisor, Dr. Nasir from LTU and Dr. McLean, and I think you from UDM.
We were provided by a client who is a 59-year-old male veteran. He had a spinal cord injury due to falling about 7 years ago while helping his neighbor. Due to this injury, he had an incomplete upper motor lesion, which is probably to be described by changes in the muscle performance. This muscle performance happens depends on the site and the significance of the lesion. One of the significant complication he had is spasticity, which is the most challenges he faces daily. The spasticity is the shortening of the muscle and the co-contractures of the flexors and extensors of the hand. This causes to shorten the tendons and the muscles and lose the elastic properties of the tissue and have frozen joints and usually spasms. His ranges of motions is very reduced in his hands and the fingers when he has a frozen joint, where it's a little bit better as you go distally to the shoulder. Proximal to the shoulder, and he has a good range of motion in his legs and his section. The client currently takes biclofen, which is muscle relaxant, which is a common drug that patients take for spasticity to relax muscles. The other treatment, widely accepted treatment, is the passive stretching. The passive stretching is to apply a sustained stretching on the site of the spastic muscles, spastic joints, and focus on activating the contractions of the affected muscles. The client does not have the means to apply that kind of stretch and could not afford physical therapy, which what the client take to take that kind of treatment.
So, as Malak mentioned previously, our main focus or aim was to target the muscles of the fingers and joint and muscle of the fingers. So our initial concept was to stretch the fingers and So we came up with this device. Basically, the device consists of 5 different components. The first one, which is the 3D printed box, which contains the circuit and the pump. The circuit has the Arduino board, which is controls the 3 valves, different valves. 2 valves go directly to the ball to control the inflation and deflation of the ball, and one valve controls the vacuum air of the whole system. And the shield also controls the rate of inflation and deflation as well. So the second component of the device is the handles. They take the shape of a joystick, and the function of joystick as well. They can go forward and backwards, and as well as the third component is the balloon. We came up with a design that accommodate and fits his conditions. So because his hand deformed and fingers deformed in different ways, so we came up with a design where you can be more effective and more easy for him to use and grab onto it. So the balloons, we had the latex layering. We used 3 different methods to do the latex. We 3D printed the mold, the ball, as you can see here. And we used 3 different methods to do the latex on it. Latex, basically the material we painted. So the first one, we applied thin layers of latex on the ball. We painted with a brush, craft brush. And the second method is basically dipping. We dip the mold inside the latex. And the third one is we created a cover for the ball, where we put the mold and the cover onto it, and we pour the latex in. But the result wasn't very insufficient and wasn't very good. Due to the tremendous time we spent on this, we had to come up with the alternative. So alternative way we used the normal balloons, 12-inch balloons. So the fourth component is the attachment. Because we couldn't do the latex on the same shape of the balloon, so we did the cover to take the same shape as the football. So as long as you build the balloon inside the cover, it's going to take the shape of the cover. So we came up with used spandex material to attach his fingers to it as well, finger straps. And the last component is the armrest. Basically, because our client spends most of his time in bed or in his wheelchair, so we designed an inclined armrest to accommodate his wrist deformity and as well as for his comfort to put it around his wrist. So the function of the device, basically, you switch on the device. As you can see, we designed the switch to be long, so he can push it easily. Because his hand, he can't control his hand very well. So when you switch the device on, it's going to calibrate and vacuum all the air up, and it's going to deflate both of the balls. So after a few seconds, the right hand will inflate, the right ball will inflate, and once he pulls his hand, either one of his hand or both of his hands back, it's going to deflate the right one and deflate the left one, and he can do it back and forth with time intervals.
We did the EMG testing to see the muscles activity in both active and passive stretching. We used the EMG work software, and we placed 5 sensors on 5 main muscles that moves the fingers and wrist. We collected the data in 3 trials when relaxed muscles, active stretching, and passive stretching. The graph shows the 3 trials and 3 different tests. The red activity is the relaxed muscle, the blue is the active, and the green is the passive. For the first one, we did the finger extension, which is basically as you clench your hand for active stretching, and also for inflation of the ball, which is for passive stretching. And as you can see, we analyzed the signals, and we found that for both passive and active stretching, we have good muscle activity in both. Also for the finger flexion, which is the clenching of the hand or the deflation of the ball, and also wrist extension, which is pushing of the wrist outward. Because this exercise triggers muscles activities by extending the length of the muscles and tendons, on the long run we predicted to minimize his spasticity and improve his condition. The recommended use, we worked with the nurses to book a schedule for the client to use for his comfort and for best benefit. To use the device for 15 minutes, 3 times a day, 3 times a week, and to use heat pads on the muscles of the hand to relax the muscle and have more effective exercise, and have rest between periods as not 2 hours to delay the muscle and have spasms. The outcome of the long passive stretching on the long run is to have reduced spasticity on the spastic joint, and to have improved range of motion, and it's affordable option for them in place in his home area.
So the responsibilities was laid on us, LT2. Basically, we designed the ball, molded the ball, and we did the latex. We did the latex and the alternatives as well, and the attachment. The design and fabrication of the attachment as well, the armrest design and device function as well, and the client user manual. We were responsible for that, as well as the testing. The UDM team was responsible for creating the pump, doing the pump, start the pump and the circuits, as well as the device design and the fabrication. The 3D printed box as well, the armrest fabrication and the device paint. They paint the device, and as the client required to be green, money, and yellow, so they painted that according to the client desire, and as well as the commanded user.
Feature consideration for the device, improvement we have into the device is to have a hand mold specifically for the hand. So instead of an inflatable ball, you could have a hand ball that accommodates each finger deformity. Another one is control setting of inflation deflation. The current setting on the device is to inflate until a specific size that he's comfortable with. Control setting on the future to have it is to control how the speed of the inflation could happen to each client. In the future also, there's a research opportunity is to go back to the client or any client is to have a research done to measure his spasticity, to measure the improvement of that spasticity. Also have a universal fit. Our device was custom made to our client. It was handmade and for his hand measurement. To market it to a larger population, a universal fit would be better for any device, and also user friendly to minimize the help that the client get while he use the device as much as possible. I would like to thank Dr. Jeffrey Moussa and Dr. Eric Mayer for their help, and also James Minders from the mechanical department and the current foundation for their funding us. This is our references for spasticity and any questions.
You didn't include a timeline of execution.
What is it?
Timeline of execution.
Did you test on the actual patient, or you only test on yourself?
As an EMG test, the signals we tested ourselves, but the client been using the device this whole week, and he's been feeling really good about it. And I talked to him, and because I've been working with him to adjust the finger attachment to make it more comfortable, and he said it's the kind of stretching that feels good.
So let me put something maybe later. So it's nice to see something in your sliders, like to see this feedback from the patient actually using the device, right?
Actually, he loved the armrest as well.
And then also, I'm still, because I don't know because about the project here, maybe nice to see a picture or video of how this thing works and all those things. Do you have a video?
We have it, it's compressed and it's blurry. We took it when we were demonstrating the video, but when over the sending, it kind of got blurry. We can play it, but I don't think you're gonna see much with it.
What were kind of some of the regulatory aspects of this project? Did you have to be concerned about working directly with the patient and actually giving him a device that he's using now? Did you go through any kind of IRB or something like that?
So when we were providing the client from UDM, they told us they already did the URB and the client approval, but we did the IRB, submitted an IRB from our university also. And we didn't have to really, they told us not to have to worry about us because they already had an agreement with the client.
So that was for the kind of assistive device that you were making, or was the IRB approval also for doing testing, like EMG testing on the patient?
The IRB was basically actually for him to use the device that we're providing for him, and also actually going to interview him and have this personal questions, pictures, and whatnot, and client information, patient information. That was it.
That would be something that you should mention during your presentation, or it should be included in the report as well. I mean, everybody wants to know that you had the institutional review board approval.
Can I find out what was your responsibility amongst yourself?
Yes, I was responsible for the designing the wall and the fabrication as well. And we were we worked together on most of the responsibilities.
What is the attachment design?
The attachment design, basically, when we tried with the latex over and over and over, we spent so much time on it. So we decided to
How
go
much
with
time did you spend?
So I'm gonna think I'm not
The latex, the usual latex layering, it usually takes from 4 to 5 hours. To complete one in 24 hours for it to dry. And we had a few models to work with.
How many?
We had around 3.
yeah, great.
We didn't, yeah.
4 days of work?
Sorry.
4 days of work?
No, we did like more than one. Like we were repeating everything over and over because we use 3 different methods. So you can imagine every method we use it like 4 times to see. Usually I take with me home and I like to put it for home to work on it.
The challenge was actually having a uniform and even layers going around. When we did the layering, when we tried to inflate it, it inflated just the thin part and the thick part wouldn't inflate, or it's just too thick. When we do it too thick, it's just too thick to inflate. It doesn't have the power to inflate it. For the layers.
What's the purpose of your testing? I don't understand what's the purpose of your test that you did.
For the testing was to have basically, so when you do active stretching, you actually exercising your muscles. When we wanted, because the client wouldn't be activating any of his muscles.
Why is that the case? If he has spasticity, isn't his muscle constantly contracting?
Well, that's what we wanted. We wanted to see if we actually.
Not stretching, it's just going down. So we need, that's what the physical therapists usually do. They go there and they move fingers. So the physical therapists usually they go and stretch the fingers, and which is they apply passive stretching to the fingers. That's what the device kind of trying to reach or.
But I mean, my understanding was that one of his arms is contracting, the other one is stretched out.
Stretched out.
Yeah, so both either way. So if you have his hand like one of them is like this, the physical therapist, he doesn't have physical therapy. That's one of the challenges as well. He's not getting better, he's getting worse. So that was like one of the problems as well. So one of his hand like this, one is like this. So the physical therapist usually, if he has one, they're just gonna stretch it. And with this one, they're just gonna open it. They're trying to stretch to activate the tendons and the muscle as well. So that's the device was trying to reach, to activate and exercise the muscles.
What we saw with him also by observing him, actually his thumb has a good range of motion. What we saw is he actually uses his thumb while his elbow to press on the thing. So the thumb is in constant exercise, constant stretching to stretch on it. So, but basically, because he had actually exercising his thumb and it has a range of motion, so that's further evidence that actually if we started to apply that kind of motion to the fingers, that over time we will gain mobility in his
So I'll come back and ask you, what were you trying to show me?
Trying to show that our device activate the muscle as the physical therapists do. Like we did passive, where you control, like you clench by yourself, no one else helping you. Active, sorry. So the muscle is activated. The passive, which is the physical therapist usually do by activating by moving his hand or finger, activate the same muscle. So when we use our device, it's the same. We got the same response as the physical therapy or therapist would do.
What are the 3 graphs?
The first one is the extension of the fingers. The second one is the flexion of the fingers, and the last one is the extension of the wrist.
Because we have 2 different, both of his hand, one is like this, one is like this. So we try to do both of the situation to see the muscle out working or not. And compared to the relaxed one, which is the red one, this is the relaxed muscle. He's not doing it.
Did you ever do a test with the EMG sensor on the patient itself?
No.
But we were there when the work care was there, and she was stretching his hand, and he felt very good about it.
The testing we did is with measuring his range of motion in each finger and see how big is his range of motion and can we move it if we apply passive stretch.
Yeah, we work with the client on different levels, like from last year to this, from last semester to this semester, we visited multiple times to get some data and some measurements.
No, I mean, I guess my comment on this graph, this is hard to interpret. You know, I mean, possibly a more, can you think of a more useful way you would present these data than just the raw signal?
We could like separate the graphs. That's gonna.
Well, one of the trials we did is actually at the same time clenching and clenching and relax, clenching and clenching and relax. But we had too much data into it, and that we didn't know when we were analyzing the data, we didn't know when is the clenching and when is the unclenching. So what we did is we start as a relaxed muscle, and then once we start the test, wait a second or two, and start to do the clenching extension or the clenching of the finger, and then stop the test to see the activation of the muscles.
So in all of these cases, the electrodes were on all the time, or?
Yes. The EMG sensors.
Yeah, but you didn't take those off?
No. We left it there.
Yeah. So, I mean, I guess, just for future reference, I mean, you might want to think about something like integrating these signals, or looking at frequency content, or you know, power spectral density of the signal, and get some overall number out of that, instead of having me try with my eyeball to figure out, you know, which signal is like more activity or less activity or these things.
Well, but the idea behind the testing is to see the activation of the muscles. We're not trying to measure like how much is activated or how much. We're trying to see the activation of the
You did it on
muscles.
yourself, you didn't do it on the patient, so it is all sort of relative, right? You're trying to get as much information out of it as
That's
possible.
what, yeah.
How fast does it inflate?
Until the client, we demonstrated with the client. At first we had a normal inflation, but with the client, I'm not sure about the number. We set it up to a number that is comfortable for him, one per MRN.
3.5 seconds.
It inflates to its maximum in 3.5 seconds?
Not as maximum, it's just the
like
size that is
the size of the
comfortable.
signal. And he can change it. Basically, you can program the circuit again and increase the rate of inflation.
Oh, so now, okay, this is even more confusing because all the axes are at different scale, right? So now I'm saying 2.5 seconds at the top and 2.2 in the middle and 5.7 on the bottom. So
These are
even a little bit more difficult to do.
because these are different tests. So the first one is different than the second one.
Oh, no, it's different. Sure, it's different. But if you want to compare results, you know.
Actually, we're not trying to compare, sorry.
Compare on the same graph.
Same graph, not with the graph for first and second. No, we're trying to compare like the first graph when you see the relaxed and the active and the passive. Is it working with the passive or not? Is it that muscle activated with the passive?
Yeah, but you don't specify which muscle it is, for example.
Well, think of the muscles.
So they.
Go back to that. Okay.
Yeah.
No,
These are the muscles we track.
Yeah, but there's only 3 traces there, right? So you should have had 5 traces if there's 5 muscle groups.
So I guess I'm just not, you know, I know you guys are doing research, but so the first graph represents 1.3 seconds overall, right? And the second graph represents a second, and the third graph represents about 1 second.
2.5 and 5.7.
Yeah.
So.
You know, I would just encourage you to put things, you know, not starting at 3.9, rather it's 0 being the beginning of the test, right?
And this is important because it's other reports, so you have to submit that, and that's a significant portion.
So if you're going to do it, put everything on the same time scale, everything starting at 0. Here's the start of my scan, here's the end of it. And then have it all, so you can compare that, so that I can look at muscle group 1, 2, and 3, even if you're not going to do the power spectrum or whatever, put it aside, but have at least three graphs kind of, on the same time axis and the same chunk, so that I can look at those signals and make some kind of comparison between them. Right?
Any other questions?
You guys can ask questions too. It's okay. It's allowed. All right. Thank you. Go ahead.
All right, hello everyone. My name is Seth Klein.
I'm Brandon Churches.
We are both seniors in the biomedical engineering program. Our advisors were Dr. Eric Meyer and Robert Fletcher. For our project, we focused on the reduction of lateral shifting of the driver while driving the Blue Devil Motorsports hybrid car. So how did we get here? We were approached back in Projects 1 by Professor Fletcher and the captain of the team with the idea that we could join. They wanted a biomedical team to join them, bring something new to the competition that they really hasn't been focused on before, to try to help the design portion of the competition. And after talking with the captain of the team, we found out that the biggest problem that the drivers had when they were driving was they were sliding a lot, especially during cornering, slamming into the side of the car. They would end up with bruises, scrapes, scratches. So Brandon and I both agreed that the best thing we could do to limit that was build a seat to hold them in place, to stabilize them.
Last year they actually did not have a seat. They only had a few foam pieces in there to hold them and to stop them from hitting the sides as hard. So what is the Formula Hybrid competition? It's a competition that started in 2006. That's an international competition. It started in Dartmouth College. It's where students come together to design and build a Formula style hybrid race car. It's held at New Hampshire Motor Speedway every year in end of April, early May. This year it was held from April 27th to April 30th, so it just ended yesterday. The team got back today. So what happens at the competition? Basically there is a few different portions of the competition. There's the design and project management portion, which is where the team sits in front of business people and explains what we did with the car, why we did it. The project management portion is where we explain how we got through obstacles, things that we had to change, what we did to come together to overcome problems and things like that. So these two portions are kind of where we would be most useful as the judging aspects. So this is where we'd be able to put input on the car. The rest of it, there is dynamic acceleration. There's dynamic testing, which is acceleration, autocross, and endurance, which this is the autocross portion real quick. This is a video taken from Yale in 2013 of them actually driving through the grass. It's basically just the car being judged on three different things: acceleration, deceleration, and cornering, to see how well the car handles. This is a pretty long video, but there's just a quick clip. It's just a very short track. The acceleration portion is about 75 meters, where the car just goes in as straight as line as possible and get up to as fast as speed as it can. And then the endurance portion is the last part of the competition, which is a 44-kilometer race, basically, and to see how well the car lasts over a long time. So, for our seat, we decided to come up with a few design parameters that we wanted to meet as a team. Firstly, we did not want the seat to somehow obstruct the driver's view. That means pushing them too far down in the cockpit where the front of the handlebars were in their view, or somehow putting them off position where they can't see very well. Second is the seat has to be able to accommodate multiple drivers. 4 different people have to drive the car, so it has to be able to accommodate different sizes, and not all the drivers are the same size. The third thing we wanted to do was create a seat that made a safe environment for the drivers. That includes while driving and if a crash were to happen. That way the driver is kept in their position, they're stopped from hitting the car and hurting themselves. The next thing, it has to be able to withstand speeds up to 50 miles an hour while driving the car, so it has to be strong enough.
All right, so getting into a little bit more of the finer details for our seat design. One of the big things that that we found was having a seat at about 120 degrees would give them a very stable seating position. When we were looking at 130 degrees, we found it was roughly the best seating position, but being leaned that far back actually blocks their view of the road. So 120 is as far as we can go with that while they can still see the track. Another reason that we went with 120 degrees is it brings down the windbreak so the car can go faster. Another thing we had to work with was easy access to the rest of the car. We had to have a seat that could be taken out quickly and put back in quickly because there are components underneath that they would need to work on. That way we could spend as little time as possible taking the seat in and out. Quick egress, getting out of the car quickly just in case there's any problems. And then the last one we have was clearance of the driver's head, which we'll go over in more detail shortly.
Also on the 120-degree angle, how we got to that decision is we were looking at the forces that would be applied to the body. So we did some preliminary testing with pressure stat paper just to see the changes of forces when you sit at 90 degrees and sit at 120 degrees. Basically, as expected, you can see that when you're sitting at the 120-degree recline, the forces on your body are more distributed. So you're not as likely to hurt your spine as if you're sitting at that 90-degree angle. Let's say like you hit a hard bump and this whole car jars, there's a chance you could hurt your spine. With this, it's a little more distributed and less likely for injury.
All right, getting back into the head clearance. For the rules of competition, there are a couple of things we had to do. We had to make sure that there was adequate head clearance. As you can see from the blown up version of the driver's head, the green arrow indicates the head has to be within 6.3 inches of the top roll bar. The 2 yellow arrows are the planes that the head has to be 2 inches under in case of a crash. That way it limits the chance of injury to the driver. And the other thing we had to worry about was driver egress. Driver egress is being able to get out of the car. At least for the competition, they wanted it in less than 5 seconds, just in case there were any problems. If the car caught fire, or if there's a crash, they can get out and get away from the car, just in case there was any problems with it. This is Lawrence Tech's team from a couple of years ago. What they have to do is, from a seating racing position, buckled in, they have to be able to unbuckle and get out of the car within 5 seconds.
So after we figured out our design parameters for our seat, we needed to start looking at materials. So our main 2 things we came up with was that the seat needed to be lightweight and high strength, obviously to hold up during the racing, and also the lighter the seat is, the lighter the car is, the faster you go. So those are our 2 main points. After that, we came up with availability to us, along with fatigue resistance and fire resistance. Fire resistance for the fact that if the car catches fire, you don't want to be sitting on something that's on fire. And then fatigue resistance being the fact that this seat is going to be used during testing of the car, it's going to be used during racing. There's a lot of vibrations happening. You don't want the seat to fatigue too fast. So we put in, thanks to Professor Lee, the CES Education Pack software, we put in tensile strength and density being our two main parameters for material, and we came up with 3,000 different materials that can be used. So we narrowed that down by adding in a slope of 1 and kind of looking at what on the top line of this is the best materials for these 2 types of properties. You can see we limited it down to about 8 different materials, which as blown up, you can see, obviously we're not going to use diamond availability purposes, not possible. There's a lot of carbon fiber. Actually, every other material up here is carbon fiber in some instance. The one we ended up using is the epoxy high-strength carbon fiber. The reasons is actually availability, and because the higher strength carbon fiber you see up there is actually about $250 per kilogram, while the high-strength carbon fiber is only about $30 per kilogram, which is more likely to either, if we need to buy it, or if it's going to be donated, someone's more likely to donate that material to us. And that's where a big portion of this came from the availability, because of previous sponsors of last year and years before that was Plays on Carbon Composites, and this is what they've donated to us for many years going, so it was a fairly easy avenue to get access to this material.
All right, so now that we know about the material we want to make the seat out of and the parameters that we had, we get to seat manufacturing. Because we have to have a seat that's going to be usable for multiple drivers, and they're going to be different sizes, they're not always going to be the same body type, we had to come up with something that would work for all of them, which is why we started with the pre-foam seat kit. What it is it's a giant beanbag, if you will, of beads that you put resin into, and after about 15 minutes to a half hour of activation, you mold it into the cockpit, and you have the driver, in our case we use the biggest driver, sit in it. He has to sit there for 45 minutes so it molds to the shape of his body. After that he can get out, but the seat kit has to stay under vacuum for about another 7 hours for it to finish hardening. From there, we went ahead and we put Bondo along the surface once we got it out of the cockpit, and sanded it down to get a smooth finish. And after that, we laid the fiberglass, which we used because it's really easy to get molds out of. The mold that we got was our negative. We used the back of that, which would then become the positive and the front of the carbon fiber seat.
We sanded this down even more, and even added more Bondo to smooth out, so that it would be a perfectly smooth surface to carbon fiber off of. So this is our final product actually in the car. We ended up making two different seats. The first one we did a 6-ply bi-weave carbon fiber, which ended up to be really strong like we wanted to, but also rather heavy. So we went back and looked at it and realized that we could use less carbon fiber and still get the strength that we needed to make the seat. So we ended up using a 3-ply bi-weave carbon fiber. As you can see, this is the actual seat in the car at competition right when we were going to the design portion.
That brings us to testing. So the way that we tested, we found an application on our phones called Sensor Kinetics Pro. What it does is it uses the sensors that are already in your phone, and it records data off of them, and you can export it. To make sure that we could accurately gather data, we used two phones. We put one on the driver and then one on the seat. And then we would subtract the seat's data from the driver to get just the driver's movement in the car. And that brings us to the graph that we have. This is a test with the seat at 25 miles an hour. Unfortunately, we weren't able to test with the car because they never got it fully running, even at competition, so we did this testing ourselves. The average that we had for our acceleration was roughly 0.5 meters per second squared, with large spikes with standard deviation.
So the bottom and top ones are the negative, positive standard deviation, and the middle one is the average. It's looked a lot better before coming to the screen.
And then we did it without our seat and just the mock-up that we made, which it simulates what they had last year with just having the firewall and padding. The average acceleration for this was between 2 to 3 meters per second squared. And the peaks are much higher for longer durations, so there's much more acceleration. There's not a whole lot to stop them from running into the sides of the car. And both of these are at 25 miles an hour, so at 50 miles an hour, the acceleration will be much greater and there's a greater chance of injuring yourself. Here's a side-by-side comparison of the two. So now that we've heard all this, what does this mean? It means that the seat that we created limited the amount of movement that the driver had while still being functional, like not preventing them from getting out, that kind of thing. So by limiting the movement of the driver, we're able to make it both safer for them and reduce the lateral shifting they experience while they're doing driving in tight corner. A couple of other things that we did. We practiced egress testing with the drivers. Each driver did 5 trial runs. And within those trial runs, the average was 5 seconds. There were some that were above, some that were below, but with very little practice, they were able to meet the requirements of the competition. We would have done more, but they needed to get underneath the seat. They needed to work on the electrical systems. And the other thing we did was we got driver feedback for each seat. For the first seat, we had all the drivers sit in it, and they filled out a questionnaire. The general consensus was that their elbows were hitting the seat. There wasn't enough clearance for the elbows when they were in their driving position. The seat was rough. There wasn't a nice smooth finish to it. The leg support was actually too long for most of them. It hindered in the process of getting out of the car. And for the smaller drivers, they needed more padding because we made it bigger, a little bit bigger. There was still room for them to move around in the car, or in the seat. With the second seat, after taking those things into consideration and lowering the amount of plies that we had on the seat, we had them practice or sit in it again and give us feedback. It was smoother. The elbow clearance was there, so they were happy about that. The leg support was a bit shorter, and it was more of a snug fit for the drivers. Our biggest driver, it was a little too snug for him, but overall, the second seat was a little bit better. If we had more time to do more seats and more materials, we would have addressed as many of those things as we could. Where does that? So now that we've heard all the data and feedback, that brings us to our conclusion. The carbon fiber seat that we created did end up reducing the lateral shifting the drivers experienced, especially during cornering. The drivers were able to get out, which was another, within 5 seconds per competition rules, which was another of the big things that we had to work with. And then where we could go in the future, actually testing with the running car would be nice, but other things we could do, add in a Hans device or some kind of head restraint so that in case of a crash, there's less whiplash, less chance of injuring the neck or the spine in any way. Or another thing we could do is add in a dynamic pressure mapping system so that we can get constant feedback of where the pressure is on the body and reinforce those areas.
So a quick summary of actually how we did the competition. We ended up 8 out of 27 different teams. We never actually made it on the track. We could not get past electrical inspection or mechanical inspection for that matter. We actually didn't even make it to mechanical inspection. We were missing some major electrical components, but we did really well for the design and project management presentation. The judges really liked us. We had a lot of good talks with them, and we were able to get 8th just off of those 2 presentations without even making it to the track. So that's kind of the dynamic events part. Didn't even get to do. Actually, only 2 teams made it on the track, and 1 caught fire.
Which is why egress testing is important. So roles and responsibilities. Brandon was working with research, the pressure testing that we did. He was in charge of the group notebook, the seat fabrication lead, and he did the presentation design. Myself, I also did research. I was in charge of the website that we have. I was the testing lead and the written report. I will be doing the written report design. As for timeline and cost, starting back in January, actually, putting everything together, we finished our second plywood mock-up at the beginning of January on the 11th. And as we worked our way down through the rest of the semester, the major things that we hit were getting the seat mold done in the middle of February, getting down to getting the first full seat done at the beginning of March, beginning to middle of March, getting feedback on it, and then getting the second one done in the middle of April, and then getting final feedback and testing done at the end of April. As to cost, the things we had to pay for were the seat kit, bondo, and the bolts for the seat itself for the car. Our total cost ended up being $430, and that money was given to us by the Kern Foundation and from the hybrid team.
So at this point, we'd like to open up to any questions.
The fiber reinforced with epoxy, and is it long fiber, short fiber?
It's a long fiber. It's
a line?
yes, it's 2 by weave lined. It's about, I want to say about 4 feet, and then it's probably a good 50 feet long. So you can cut off what sections you need for that. The weave, it's actually pre-weaved. It's pre-weaved, so yeah, that's where the bi-weave comes in.
You just lay the epoxy.
Yep. Put the resin and hardener together, and then put it on.
Did you test that like material properties?
We did not get to that. That was the next step we were looking to, but we do have tensile and functional testing from exactly the material that we use that we were able to find through research. And while we were at competition, we found a lot of different technical papers regarding that specific carbon fiber.
Okay. Yeah, so I have a couple of questions. You know, in the results you said a lot about better this, better that, you know. But did you measure anything not with your seat, like with the previous design? Like, I mean, whatever they use now, how do we know that it's not just as good as what you stuck in?
Are you saying from last year's car to this year's car? We were not able to because last year's car is actually not even running at all. They have engine problems with that. It does not run.
Okay, so I mean, would they have used some default seat maybe not designed?
Basically, most likely no, because of the way the cockpit is laid up. It's almost, they wouldn't be able to, how they would be sitting would be way down in the cockpit. They couldn't be able to see, and they would not, basically would not be able to get out of the car because of how high the sides were.
So I don't know if your thing is better than last year's or not.
We tried to simulate last year's, at least designed by just having the mock-up, which was just, which would essentially be the firewall and the padding that they had last year. Granted, it was still at 120 degrees. It wasn't like a straight up and down seat like they had in last year's car. But we tried as best we could to simulate, even with the change in angle, the conditions they would be driving in last time. That was without our seat in it when we did testing.
Okay. So I have a category here called presentation delivery, and I'm wondering if you guys like the project.
Yes, I did. I actually really enjoyed it.
It was a lot of fun.
So that's the first time I saw either one of you smile this whole time.
Well, I mean, it's a little nerve-wracking.
Yeah. So I'm glad to see it.
Yeah, no, I really enjoyed it. I learned a lot of different things that I really never thought I'd get exposed to. I really did enjoy it, and it was cool working with the car as well, because we did put on a lot of time, not just in our project, but working with the team and working with the hybrid car where we were able to.
Loosen up and get the hands up.
We have a question.
Yeah.
Do other teams use like commissionings, or is that like a finance?
When we were looking at the other cars this year while we were there, the other teams, some of them had carbon fiber seats, some of them used cushioning, some of them didn't even have seats. There were a couple of cars that were just a frame with an engine on it. But it varies for what works best from team to team. Like last year, they only used cushioning for Lawrence Tech's car. But this year, we have the seat and we have cushioning for it. So I guess it really depends on the school, and their design. So long as it doesn't hinder them getting the egress process,
So if this project was, and it happens every single year of the competition, we were going to run next year, is there a plan to continue to keep the seat in there? And if they do, are they going to build the new seat, or are they going to use the one that's already available?
We were working off the, not really assumption, but the idea that the team was looking for. Moving forward, they wanted to keep the same type of chassis build, which would mean they keep the same type of recline so they can use the seat again. Obviously, there is some updates and things that could be done with that seat, and a few different ways that it could go to make it safer or even better for the drivers.
Like what?
Again, more for one of the drivers, their complaint was their back was a little too flat. It wasn't as rounded to their back, so it was kind of stiff on them. It could be.
Can you put cushioning on there?
Yes, we put cushioning more around the bolts, where the bolts were coming through, because
I never saw a picture. Do you have a picture of like a complete?
we had that small one. We weren't, because of the fact that we never actually raced, we didn't fully cushion it, being the fact that we were trying to help the team get running.
Or do you take a picture of your final product?
I mean that is, where is it?
Next slide. Next page.
Okay.
But that's
So yeah, that's our final product. Because of our Zach, the bigger driver, the one that we actually took the mold of, he was such a tight fit, we could not put really any significant cushioning in there because he would not be able to fit in the car. It would not do anything for him. That's where we would want to make next time maybe possibly a little bit bigger seats. That way we could line it with more cushioning. And with that more cushioning, the smaller drivers should be able to fit in it as well and be able to get benefits from it.
Can you go back to the material choice graph and explain to me what was going on there?
So basically, this is
first of all,
this.
One more. What is this?
So this is just basically a program that you look at the bulk materials. Yeah, this is just the bulk materials of everything it could possibly use. This is when we first put in the two parameters. This is the screen we got.
What parameter?
Lightweight strength.
We just put in tensile strength and density and looked at for which ones had the highest tensile strength compared to density.
So why is there a line on the next?
Because that's how we started to narrow it down.
High strength, low density.
Yeah, we moved that line up to where we wanted to limit it to about the 10 highest possibilities. So that line helps you by reducing the ones that are below it, basically. So that's how we were able to come up with those top 7.
Does that color mean anything? Why is one?
This color right here does. The red is all carbon fiber and the yellow is diamond. On the next slide, we just kind of switched the colors just so it was a little easier to see where they were.
I'm good demo next Monday again.
For your lateral shift displacement measurement, you said you used the sensors in your phone, which are linear acceleration.
Yes.
So you have like 3 coordinate axes.
Yes.
How did you combine that data? Was it like x minus x, y minus y, z minus z, or did you use a vector magnitude and subtract that?
We focused on using X by itself.
Oh, you just looked
Just
at
looking
one
at
of
X,
the
yeah.
Okay.
Yeah, we had looked at the z and y coordinates, but there was almost no movement, or at least nothing significant that would show us anything was happening in both seats. They were when the seat went up and down, so was the person. There wasn't much movement in that, so you really couldn't tell which.
So you did look at the other two?
Yes, we did look
but
at
you just
them.
didn't show it.
Yeah, we didn't show them. They weren't.
So with respect to the driver, what is X?
X is left and right. So in these graphs, where are they?
They call it lateral.
So in these graphs, negative is right and positive is left.
Okay. And so you're saying that the person was so secure he was bouncing up and down and all. That's
When
what I see.
there was bouncing, it was with the whole seat. That was it. They were sitting on the seat. There wasn't any up and down change compared to the seat. Now, yes, when the car was bouncing, the person was moving up and down, but it was with the seat. There wasn't any difference between the body movement of the person and the actual physical movement of the car and the seat.
And how did you time sync the 2 sensors, the one on the person and one on the seat?
What we did to start off is we rested the car for about 10 seconds, and then we did just gassed it to get the initial Z acceleration at that point, and we used Z then to actually line everything up. And then from there, all the peaks lined up really well once we lined up on both graphs the Z coordinates, deleted everything below it, and then we had also at the end, we had a pause. So there was no movement whatsoever going on, and then we deleted everything after that pause. And so that brought everything back together.
How did you ensure that this is on the phone, right?
Yes.
The phone wasn't moving relative to the body and
We use low-pass filters to help get rid of any sort of...
So wasn't it secured on the person?
Yes.
How?
We created a nice tape thing.
But I mean, how was it oriented? Was it on the leg or was it?
No, it was right in the
It was
chest.
on the chest, the other one was on the seat, on the back side of the seat, but like directly correlated with.
They were both oriented in the exact same
Yes.
angle?
Yes.
Are you sure?
Yes.
Because you have 120-degree angle on the,
Yes.
on the seat, right?
Yep. Seat and person.
But you know that from the non-moving position.
I'm asking. If they have confidence in that thing, because if they're not aligned, then you can't compare.
Yes, I have confidence they were aligned. When you look at the angles of, we even started, before we did any testing, we actually took, our preliminary testing, we took a lot of different samples, not just linear acceleration, we did, I forget, like gravity, we took the gravity sensor and everything was basically aligned in every other sensor. I forget all the actual sensors we took, but there was like 8 different sensors that we just took all the data and kind of looked at it to see if they were in line and what actually was useful data.
Just a couple of comments. I think for a lot of the stuff that you showed, if you show it with your stuff, it carries so much more weight. So you should have taken videos of egress from your seat. You should have compared both of the seat designs and showed them side by side to see how they look different. I mean, you explained how one is better than the other, but visual method of showing it is so much more powerful than saying the elbows are higher, the things lower, and things like that. And so it's just a way to have an ownership on the work that you're showing. I mean, I understand that you have to show Yale University's video for the race, but I mean, for a lot of the other things, I think we need to include things that you did instead of taking somebody else's work.
Yeah, that was things I thought of when we got back here, but our actual seat was still a competition, and it was too late of thinking on our part.
Thank you.
Thanks.
Good afternoon, my name is Patricia Nahas,
I'm Evan McKenzie. And I'm Christopher Harris.
and we are excited to present to you Raptor 2K15. We are similar to the first team that presented, whereas we are a collaborative effort between students here, 3 biomedical engineering students, and 3 nurses from UDM, University of Detroit Mercy, as well as 4 mechanical engineers. So this project consists of a client volunteer from the VA hospital. We're given a middle-aged male who was in a motor vehicle accident over a year ago. He suffered a level C3, C4 contusion, which is a bruise to the spinal cord. You can see in the diagram where exactly the C3, C4 vertebrae is. So because of his accident, he sustained an injury and now has incomplete tetraplegia, which limits his mobility in his limbs. But we did notice that from the first time we did assess him to now, he is improved very much. Because of his medical condition, he does live in a 24/7 assistance group home living. He always has some type of caregiver or nurse's aide there to watch over him. So what he really wanted out of this project was to gain independence to perform daily tasks. He wanted to be able to feed himself eventually. He wants to brush his teeth. He wants to shave. He also wanted to exercise without the assistance from a physical therapist or an occupational therapist. Right now, he does see one 3 days a week. However, it leaves him unable to exercise the other 4 days per week. So what we wanted to do, after speaking with the OTs and the PTs, is to strengthen his upper body. This will help him gain independence. We focused on 5 major muscle groups: the pectorals, the biceps, the deltoids, the trapezius, and the triceps. By strengthening these muscles, you can promote rehabilitation that will assist our client in performing his daily tasks more independently. And we also wanted to make sure that he could use it without having a PT or OT there. So now that we have our goal of what we wanted, we needed to break down exactly what important things we needed in the design. We wanted him to be able to use it in his wheelchair with minimal assistance. again, he does have a caregiver there, so that person is able to help him in and out of his bed. We wanted to keep it in an upright position. This promotes a good posture so that when he's exercising, he can maintain that. We need it with adjustable resistance because although his mobility is very limited now, he is improving. So we want it to be able to improve as he rehabilitates. We need it storage friendly. We need hand stabilization because right now he does not have gripping strength. We need it transportable, and we also decided on the pedaling motion. Using that cyclical motion will actually help our client utilize those 5 major muscle groups that we showed on the slide beforehand. And for this, we had an idea selection. We were given the task of coming up with 100 ideas and concepts, and then narrowing it down from there. That's what it says. So now we will actually perform a demonstration of our final project. While they're getting that ready, I'll briefly talk about the manual that we created. Inside the manual, there's safety information, specs, biomechanical positioning instructions. It also includes a workout that's tailored to our client so that he can safely use this product.
So as you can see, Evan, right now, he's using our device and he's basically pedaling in a vertical motion. This is going to target each muscle as we will show in the testing stage. Also, what's so novel about our device is that it's really easy to change the position to a horizontal motion, which would target different muscles such as the pecs. As you can see when Evan changes the position, which is really easy. And now we can do it in a horizontal motion, forward and backwards. Also here, the trigger, this is basically a device that can change the resistance. So this is why our device is pretty novel because without the horizontal and vertical position, it's basically a bicycle. And we can buy a bicycle anywhere, but this allows our client to use it in a vertical and horizontal motion, backward and forth.
So after we came down to that one idea from that list of 100, we started out with some ideas. The top left image is our concept from our presentation from last semester. That was our final concept. And from there, we had some things that worked, some things that didn't. Below that are 2 of the resistance mechanisms. The one on the right actually got 3D printed and magnets were put in it, and we tested that, and it didn't do some of the things we wanted. It was very hard to make that resistance variable. So that then the UDM team was looking for a commercially available magnetic resistance device, but they were very hard to come by. And so the wooden spools was a mechanism for their gearbox design. The wood for the Legos was one of our ideas for a like how to make it adjustable. And some things fell through. And then the bottom right is our final. That's the frame that's in flying. So yeah, our final design that we came up with incorporates that gearbox there. That's a top-down image without the case around it, and it's all made. The frame's all made from aluminum T-tubing. The new resistance device that's non-magnetic is a band brake system. It came off a Nordic track actually, and as you turn that dial up to the resistance, there's a piece of webbing around that black flywheel that tightens down. So as you pedal, it's harder to pedal as you tighten it down. So that's our variable resistance. As we demonstrated before, you can move the pedals from the vertical plane to the horizontal plane quite rapidly, making both of those different workouts possible. The overall dimensions allow it to fit through a door frame and store in the corner of the room quite nicely. And then we did some testing to figure out what the minimum and maximum resistance was. So those are the torques that are listed there. As we split up the design between ourselves and UDM, they got the frame and the resistance mechanism. We took spindle outwards, so she was pointing at the spindle. So that's this top left image is from our SolidWorks design. It's pretty simple, but it allows for all those things that we wanted. The gears setup allows us to do a more natural motion for, coming inward with both hands or going outwards with both hands instead of doing some weird, like butter churny motion. This is how I describe it. The handles are made of foam that was generously donated from
Grab-on grips?
Yeah, grab-on grips.
It's a company in Washington.
That was nice. So it's nice. It's quite dense, but it's still squishy, I guess.
It's used in many exercise devices that are out on product today.
And we were looking for, since he does have trouble gripping, we had devices that he can already use in his home, like his razor and his toothbrush. We took the diameter from those and figured that that size of handle he could use. And then we have the strap that goes on it that helps keep his hand towards it since he has trouble gripping. And it works quite well for being so simple, which is nice.
Yeah.
The other big thing is that we have the ability to, again, so it's just a quick set screw that loosens it and puts it back on. And since he is in that 24-hour care facility, his nurses can help him with the setup, him getting up to the device, him changing those handles out and those kind of things. And it was designed, UVM actually has a chair that's very similar to his, the wheelchair. So the height and the width of those handles was all designed to set up based on his chair so that he would fit in it.
So this leads to the testing portion. So our testing consisted of the Delta Trigonal wireless EMG sensors, which basically gave us the muscle activities of each of the 5 target muscles. Along with the Vicon 3D motion capture system, we use that capture motion system to basically get the kinematics of the body. As you can see in this image here, this is the upper body limb model where markers were placed on the subject along with the sensors, and that gave us the data that we processed, which is going to be in the next page. Next slide. So here's our results. It's basically the kinematic angles for as you can see in the first graph, it's the elbow and flexion extension. So in this model, this is the model that was, I guess, processed out of the Vicon Nexus. So as we were testing on the bicycle that was shown in the previous slide, we were basically pedaling forward, and the flexion extension of each elbow and shoulder, as you can see here, is basically an offset, which makes sense because when you're pedaling, there is an offset from your shoulder and your elbow relative to each other. So that's just showing the kinematics of the elbow and the shoulders of each. So the next slide depicts the bicep, deltoids, pectorals, and the following slide is the other 2 muscles. So in order to get appropriate data, we had to go through a series of steps. As you can see here, we went through the EMG signal. In the blue, there's just basically the raw data that was processed out of the EMG sensors. Basically, we had to do a DC offset to align that. After that, we rectified the EMG. Basically, we just kept all the positive signals, and which basically give us the envelope of the EMG sensor signal that we want, which is shown here. In the green is basically we use the low pass filter, a low pass filter with a cutoff frequency of 10 hertz, sampling frequency of 2,000 hertz, and we use all this. We gather all this data basically from MATLAB. So it just depicts the bicep, deltoids, and pectoral. As you can see in the spikes, that's basically the muscle activities of each muscle. And the following slide is basically showing the trapezius and triceps, basically the same information. We went through a series of steps, EMG signals, rectify the EMG signal, then to later get our envelope of our device, of our signal. Last Friday on April 24th, we presented our finished product to our client who was very happy. As you can see in that picture right there, it's a group of us taking the picture, so yeah.
So from here, since this device was produced specifically for our client, but we feel it has the ability to be marketable to many other people that didn't have spinal injuries, anybody with who needs to work on their upper body, the device can be used, but there would have to be some changes that could be made to make it better for a general audience. Dimensional adjustability, so have that height between the ground and those handles be adjustable. Have the distance between them be adjustable since not everybody's shoulder width is the same. Have that crank length be changeable so that you could have him doing smaller circles to larger circles as much as he wanted. The next big thing is to improve the resistance system. If we could go back to a magnetic system, that would be great. Having more variability, as you saw, it's kind of small right now. And then if we could decrease the internal resistance of the device itself to almost have it as close to zero from the start as we could, would be the best for people who are really weak at the time they start. If we could make the footprint smaller, that'd be great. If it was more storable or could fold up somehow, that would make it even better. You could hide it away in a closet or something instead of just being in a corner. And then the lower body motion. At the start, we kind of wanted to do a full body workout device. In our time scale, or like the scope of the time that we had to produce the device, that was a little over the top. But if we could add in all that unused space underneath it, regular bicycle pedals that would attach to this device, that'd be great. And then if we could do more testing, especially post-use testing on our client himself, so to show that those target muscles actually got worked and he improved, that would be very nice to be able to take it to market with data like that.
So here is our timeline. Basically, it's a list of dates of fabrication, when things were complete. As you can see, we did have a little bit of a crunch time in the end. However, we did end up delivering a functional device on the day we were supposed to. So that's very important, and we did end up reaching that goal. And then the next slide is our division of task. While UDM were responsible for the frame, the resistance mechanism, and the enclosure, we were responsible on the device anywhere from the spindle out to the end. We also did the user manual. We did all of the testing and did communications with the client. So it's all listed there.
So this wouldn't be made possible without a few familiar faces. First off, we'd like to say thanks and give acknowledgement to our client, Mr. Steps, University of Detroit Mercy, the Senior Project Advisor, Dr. Nasir, along with Dr. Planky, who is a mechanical engineer at the University of Detroit Mercy. Also, Dr. McLennan, which is right there. Thank you very much. Our technical advisor, Dr. Meyer, who graciously helped me out a lot with the testing, so I'd like to thank you for that. Also, Lawrence Technological Fab Lab, which Evan spent a lot of time there fabricating our device, along with Grab On Works, which we just told about. We got the groups for free. So.
Pretty good.
And funding?
That was provided through the Kern Foundation.
So acknowledge them.
Yeah, probably.
Yeah, that's it.
They were on the front. There was a
It's a
image of their logo on the first slide, I think.
Okay.
Yeah, we acknowledge them in the front. Yeah.
But yeah.
So, any questions? We're open to criticism and
Constructive.
discussion. Yes.
Just Dr. Wayne.
I think with a very good demo, very good manual.
Thank you.
And great to see it's being used already. I do have a question regarding the test you showed there, the
Yes.
bike test. It seems you were testing on the bicycle.
Yes, it wasn't
the
actually not
actual-
on, yeah, it was not
Yeah.
on the device itself.
So
We
you were
basically,
targeting these 5 muscles, so in the results you showed there were all 5 included.
yeah, all 5 muscles were included. So you see biceps, deltoid, pectorials, and then following trapezius and triceps. But as you just said, it was tested on
That's
the
the
prototype.
most motion compared to your actual device.
Yeah.
Yeah, I mean, it's
Very similar.
Yeah.
to the vertical cycling motion, however, a little bit louder. Yes, not the
That's what
horizontal.
I believe Evan spoke on. We need to do further testing on this device. That's why it's still here instead of with the
Yeah, 4 days. I've got a question. So, right, go ahead, John.
Does he like it?
Oh, he loves it.
Yeah, he was very happy. Because when we talked to him throughout the whole project,
Yeah.
and UDM, we went there for their presentation to him because a lot of their grade was based on his happiness and how he felt about the device itself. So they presented to him to get his approval middle or like end of last semester. So we talked to him there, and he liked all the stuff that we were trying to do, and then he saw it. And those were all the things that we had set out to do. So he was pretty happy with that. He had some little things that we fixed this week.
Yeah, some minor things.
But yeah.
So we were able to make adjustments. So we're glad to have it a couple more days before the real delivery. That way we could make sure it's useful.
Dr. Meyer.
Are there other devices that do this type of thing, or how does yours compare to what's available?
Actually, that was one of the stipulations for this project. It had to be something that was currently not on the market, and that's actually also part of UDM's grade. They had to design or come up with an idea that's not on the market.
So what is available? And how
So
is yours?
the bicycle machines, however, not the double axle.
Right.
So what makes our design different is that you're able to do the vertical and the horizontal rotation.
And a very easily to switch the position.
The other, may I add, the other unique thing about that is on, and I know you guys know this from the mechanical engineering side, in a normal bike, when you rotate, the force keeps going forward, and this one does not. They did,
Oh, yeah, yeah.
somebody,
I forgot that one.
so it doesn't keep going forward, so he can't injure himself.
So yeah, the flywheel itself, the gearing mechanism they came up with, as you spin it, all the force goes back towards, or the momentum of the wheel doesn't drive the handles themselves.
So if he stops the handles, the momentum doesn't transfer to him.
Could you add a motor if you wanted to do like passive, like where they
To
don't
drive
have
for
to-
him?
So it would just move the arms without
Well,
any
you
muscle?
could, but it's not gonna build up your muscles as much.
It might help with range
Maybe
of
It's like the
motion.
difference between riding a motorcycle and a bike.
It can help with his range of motion, but
Yeah, wouldn't it help with just passive or?
Maybe passive, but he really wanted to build up his muscles.
Yeah.
I guess I kind of along those same lines. And you guys weren't on that team, but there are exercises, that you can strap on to the back wheel of your bike as a magnetic
right.
system built in. Or, even getting simpler, using, you showed the bike, if you actually put a derailleur and some gearing system that you could say.
You just change the gearing.
Up to the next gear, and now it's harder to do.
Yeah, I mean, that's kind of what we
Well, because the other thing that's nice, they have the bike trainers where that are like dynamic resistance. So the harder you pedal, the harder they push back. That would be nice as well. So if you're going nice and slow, it's kind of
Yeah. So I mean, just something to think about using existing technology.
yeah.
Besides that, I don't know whose house that easily fits into the corner of it. It would not be mine, for sure. So the size is a little bit.
It could get small.
I mean,
Just
yeah,
Don't
definitely.
overplay the portability of that, and how easy it is to store.
Did you measure the weight to see on the floor?
I think total we were under 50 pounds.
You didn't measure like.
We measured components.
Components.
So we measured all the pieces.
So where's
so,
most of the weight coming from? Just the stem?
Probably.
Wait, so what is
Well, the
stem?
resistance
device
mechanism is about
itself is
25 pounds.
Because that flywheel to get the inertia.
So you need a large enough base so that it doesn't topple over.
Yeah.
Exactly.
And that was, I mean, that's one of the ideas we scrapped. That was the reason, is because it was going to be heavy and away from the base, so we had to scrap it.
Let me ask you, so how was the exact exercises that you decided to focus on, how were they decided on? Because you didn't show any motivation, you just said that we have those 5 muscle groups and this motion is going to address them. Was there any like logic for that other than just like sort of like, I do it, I
mean, that's why it kind of made sense in our head, and that's why we did the testing, just to verify that the muscles
But
did
that
do
happened
that.
after. I'm saying in the design, when you initially designed, you're sort of designing for a specific motion, right?
Oh, I mean,
So
that was,
going into it, did you have an idea about
yeah,
why that motion was chosen?
Yeah,
the motion came away from us trying to target upper body muscles. So you hit a really good chunk of the upper body muscles by doing these two simple motions.
And also talking with the medical professionals, they have the PT and the OT. Those motions definitely hit target those muscles.
Is there any exercise currently that mimic or are similar to this?
Right now, he has a stand with rubber bands that he uses to exercise. I mean, it is flexion and extension, and it does use the different degrees of freedom with the rubber bands. However, it's not as stable. Like, this is more of a steady motion, and that's kind of what we're looking for, rather than having, the physical therapy rubber bands hanging off of a stand, whereas, sometimes they're not placed right, sometimes it has varying motion. And the PT and the OT, when we sat in sessions with them, that's one of the difficulties and the harder parts of the rehabilitation process.
I mean, it's a common side that I think you can sort of rely on literature or rely on data that comes from, just people who are rehabilitative work with patients to sort of say that this motion makes sense, so that you explain that there's good motivation for the design, because essentially your whole design is built on that premise, that these motions are effective, and you have to have a good motivation for that. Did you look to see if the gears were up? How long before they were up? How many motions before, or how many revolutions, how much time before they were up?
We didn't look at that for particular
What is the
testing
material?
of steel. I mean, the gears aren't meant for this. They were meant for, automotive, very high speed use. So we were, if they're designed for that, there's much lower speed and much lower, force on it. You shouldn't wear it out faster.
Have you considered any of the issues from a safety standpoint? Can you describe if there's issues from a safety standpoint?
Well,
A lot of things will probably be enclosed, of course, because as you can see, it's kind of just sticking out. But there's a lot of things that should be enclosed.
I mean, is the idea that you would always use this with both hands simultaneously? Could you use this with one hand at a time?
Absolutely.
yes. Once he gains enough strength, right now, we want it complementary because one side is stronger than the other, and we want the other side to be able to help the weaker side out.
And when we presented it to him, that's what he was interested in as well, was if he could use his stronger arm to propel his, or help out the weaker arm right now, and it worked. So that was nice.
Can you put the division of work and then just explain to me on the device itself as to what part you were responsible for as compared to?
Oh, that's nice.
Oh, sorry. Wait, this one.
It's a little general. When it says design and fabrication, I don't understand what part of design and fabrication were you involved. Trying to see.
Basically, these are the division of responsibilities. Everybody kind of overlapped with tasks also. So, just because your name is on it doesn't mean you should get all of the credit for it. Everybody worked as a team, and in the end, it's the end product.
I was just asking what part of it. So it was just the handle and...
So we did there's this spindle in here, and everything from, and then this, Good point. So there's the spindle in there,
Big
the
guy standing there.
axle, and then the gear, like the gear housings, and the handles, as well as we did the bracing for our car, right, from the frame to our car. So.
Thank you.
Thank you.
Maybe let's just take a 5-minute break, just so people can stretch out, and then we'll start after that. For
I can make up for it. I can try. Can't sing very well though.
Good afternoon, everyone. My name is Amanda Botia.
And my name is Caitlin Tingley.
Our faculty advisors are Dr. Lee and Dr. Nasir. Our technical advisor is Dr. Buakel and Dr. Honor from Wayne State University, who has given us the privileges of using his laboratories. Ladies and gentlemen, did you know that there are more MRSA deaths each year in the U.S. than from HIV, pneumococcal, meningococcal, and influenza combined? United, we are here to present our impedance biosensor for the detection of MRSA. Our goal was to develop a quick and cost-effective method to detect if a patient has MRSA. Our solution, a novel impedance biosensor, which also happens to be disposable.
So to begin, we need to understand what MRSA actually is. MRSA is known as methicillin-resistant Staphylococcus aureus. It's a type of staph infection that is resistant to most antibiotics. It can be passed through skin-to-skin contact, and if it gets into an open wound or a cut, it can get into the bloodstream and infect the liver and heart and result in death. Standard test takes 48 hours, and in that time, a patient can transmit the disease to more people. We went into the elderly care facility at Beaumont Hospital, and they expressed the need to come up with a quicker diagnostic tool to test all of their incoming patients.
There are currently only 2 diagnostic methods that are used to detect MRSA clinically. There are plate-based culture screenings and polymerase chain reactions. Plate-based culture screenings are pretty easy to conduct, and they don't cost a whole lot, but the downside is 48 hours to 72 hours for detection results. PCR takes 4 hours for detection results. The problem with them is the high cost associated with the equipment required to perform the PCR, as well as the tendency for them to result in false positives. New devices called MEMS, micro-electromechanical systems, also referred to as lab-on-chip devices, are now being used in the research development stages. When you compare these to the clinically used methods, they are cost-efficient, have high sensitivity, and only require a few hour or less detection time. This is precisely why we chose a MEMS device for our solution.
To understand the basics of our project, we need to understand the biological properties that MRSA has. There is this type of protein called an antibody that can isolate MRSA away from other types of staph infection. This has very highly specific binding, which increases the specificity of our device. The antibody that we looked at was anti-PB2A, which binds to PBP2A on the wall of the MRSA, which is used to control the MECA gene, which makes MRSA methicillin resistant. So how antibody-antigen bonding works is that only one antibody actually fits into the certain antigen, which in our case was MRSA. So it's a lock and key type of method where if you don't have the right key, you're not going to get into the lock, which is the antibody. So that makes our device highly specific. Now we're going to go into how our device is active.
This is our basic device function. Starting from the bottom up, we have a glass base with patterned electrodes on its surface. At the tips of these electrodes, where they thin out over here, that is where they are coated with our antibodies that Caitlin just discussed. Then we have a PDMS substrate that is bonded to our glass device. This substrate contains a flow channel containing an inlet and an outlet. As we flow our bacteria solution through the inlet, it goes through the channel, and then it will cross the electrodes and the antibodies. MRSA will bind to these specific antibodies, and everything else will flow out to the outlet. Since this is not able to see with the naked eye, what we will do is connect an impedance analyzer to each one of these leads, and we will measure impedance. And then we will know if MRSA is present. Our team has designed 2 different prototypes. Device A is simply a 2-lead design, while device B contains an interdigitated design. It's important to keep in mind that the left and right side of this design is not connected. Also, we have in blue rectangles here our flow channels where the solution will flow through, and then all other regions of gold that we will not use are passivated in order to eliminate the external noise and artifacts that would otherwise affect our impedance signal. In order to create our devices, we had to undergo 3 different steps. First, the glass wafer was fabricated with gold and passivation in desired regions, which Caitlin will go into further detail later on. The actual devices are shown in these images here, and they are also being passed around for all of you to see. Next, our PDMS substrate was created, and then ultimately it was bonded onto the glass device.
So like Amanda said, the first thing we had to do was fabricate our electrodes on our glass surface. What we did was we obtained a glass wafer, and we had gold evaporated onto the wafer using a thin film deposition. Next involved a lithography process in order to designate the specific areas we wanted the electrodes to be on. Then there was a wet etching process to remove any unwanted gold. We repeated the same flow process, but instead of using gold, we used a silicon oxide, which is shown in green up here. And this is ordered, like Amanda said, to passivate the regions that we did not either have something flowing over or soldering to. The last thing we had to do was fabricate our flow channel. We created a mask at Wayne State University, and we brought the mask back here to actually pour our PDMS polymer onto it, cure it, and we were able to peel off the mold to make our flow channels. After we had both the electrode pattern gold and we had our flow channel, we were able to bind them together. We oxygen plasma treated both the PDMS and the gold bottom, bound them together for 10 minutes. And we found out that device A actually proved to have better adhesion because we had more PDMS substrate actually be able to have on the glass, due to the fact that device B had to remove more of the PDMS substrate to actually get to the gold pad to solder onto.
As for testing, first we conducted impedance testing on our device by using a PBS solution. The solution was flowed through the device using a constant 0.5 milliliter per minute flow rate. A syringe pump was used to accomplish this consistency. An impedance analyzer was connected to the device as shown in the previous slides. And to do that, we connected wires to the device and then connected the analyzer. We took a frequency sweep from 0 to 100,000 hertz to obtain our data. Our impedance testing consisted of 3 parts. For the first part, we flowed 4 different concentrations of PBS through our device, 1 concentration at a time. The results are shown in this graph here, plotting frequency versus impedance. Since PBS is a saltwater solution, as we flow more ions through our device, we are essentially shorting the devices together, and we will be seeing a decrease in impedance. So when there is no flow through our device and our device is static, we have an open circuit, hence an infinite impedance. So this graph proves this by showing as we increase the concentration, we have a decrease in impedance. Next, we took our results and plotted 3 different frequencies to find the correlation between PBS concentration and impedance. The graph proves that we have an impedance that is inversely hyperbolic to the ion concentration. If our device were to be tested with MRSA, when the binding of the bacteria and the antibody occur, we would be adding an insulation layer on top of our electrode. That would be the opposite effect of what we get here. that insulation would cause a decrease in conductivity of the electrode, resulting in an increase in impedance rather than an increase. Part 3 of the impedance testing was where we took a 1x PBS solution and we had it comprised of steel particles. A magnetic platform was added to this setting right under our device. So as we float the solution through, the magnetic particles would be captivated by our electrodes through magnetism. And basically we use our 1x PBS as our control and then show the steel particles decreasing the impedance following the same concept I described in part 1.
So to understand, make sure our device actually worked, we need to validate the antibody that we've chosen, because you can get multiple variations of PB2A antibodies. So to do this experiment, we need to conduct the testing at Wayne State because we cannot bring MRSA onto Lawrence Tech's grounds. For the main components of this experiment, we needed to have the bacteria, our antibody, an Alexa fluor, and a fluorescent microscope. Alexa fluors are used to bind to the antibodies, and when our antibody binds to MRSA, the fluor will fluoresce under a fluorescent microscope. To begin the experiment, we created 3 different concentrations of our antibodies. We had 1 to 1,000, 1 to 2,000, and 1 to 5,000. And this was done to show that with different concentrations of antibodies, you can have different bonding occur at different concentrations. And we tried to find the concentration that has the maximum amount of binding occurring. We pipetted a solution of bacteria, antibodies, PBS electrophores in the centrifuge tubes, and looked at each individual concentration under a microscope. We looked at 2 different types of staph infection, MRSA, and then MESA, because they almost have the same genetic makeup, except the MESA doesn't have the MEC aging, which makes it so it's methicillin susceptible, can be killed with killed drugs. It shows that our antibody was actually quite specific because it can differentiate between 2 very similar families of staph. And if you look at our results section, you can see 3 pictures below, and these were the pictures we took from the fluorescent microscope at our 3 different concentrations. These are the only pictures of our MRSA because when we looked at MESA, nothing would fluoresce, so there was just a black screen. And if you look, we see we have slightly more binding at 1 to 2,000 concentration, but for the most part, we saw binding at each individual concentration. So we were able to prove that our specific PB2A antibody that we purchased from a supplier does actually differentiate between MRSA and MESA, which was good. So the next thing you have to do once you have your antibody is you have to immobilize it on the gold surface so that when you flow something over your channel, that the MRSA will hopefully stick to the antibodies. So we used a molecule called EDC to immobilize them. And this chemical binds to a carboxylate, which is on the other chemical called NHS, and an amine on the antibodies to actually bind to the gold. To test our mobilization process, we coated our devices with EDC and NHS and then applied some antibodies. And we looked at these devices under an atomic fluorescent microscope. As you can see from our picture on the right, that's the picture we obtained from the fluorescent microscope. We only got 1 result to actually come out, and as you can see, there is something on the surface, but it's kind of hard to tell what it is because it is very condensed together.
To sum up our project, our biosensor is novel in that no other impedance method exists to detect MRSA. Leading to today, we have designed and fabricated our devices, we have validated the impedance mechanism of our device, and we have verified the specificity mechanism of the device as well. Last, we have immobilized antibodies, as Caitlin just discussed, but we still need to conduct a validation test for them. Caitlin and I received our OSHA training in January. We then started the design phase in February. We decided to design and fabricate 2 devices to avoid future modifications of the device. We finished wafer fabrication in March, as well as our antibody testing simultaneously. In the beginning of April, we fabricated our PDMS and were also able to complete device testing. Because there are only 2 of us working on this project, we planned and worked on most of the tasks together. Our tasks are outlined in this M diagram shown here. We both completed the OSHA training and we designed the device together. Even though we're working on all the aspects together, each one of us is an expert in a certain area, and that's the area that we oversaw in the project. I was in charge of fabrication and impedance testing, while Caitlin was in charge of antibody immobilization and antibody binding testing. We communicated through text, emails, and our shared calendar.
So some of the things we would like to do in the near future is try to do some console modeling of the fluid flow of our device. And we would like to do some more mobilization verification and hopefully conduct our flow-through testing with actual MRSA. In the future, we could look at trying to integrate the impedance analyzer onto the actual device and possibly creating packaging for the device itself. Before we conclude, we'd like to just have a few acknowledgments to people that have helped us along the way. We'd like to thank Wayne State University's SSIM lab for providing us with the materials, the tooling, and the training in order to complete our task. We'd like to thank our faculty advisors for guiding us through the entire process. And we would like to thank the Lisa Foundation for providing us the funding in order to complete our project. At this time, we'd like to open the floor to any questions, comments, or concerns. Questions?
If you produce this commercially as a medical device, what class of device would it be?
It would be a question.
Just because it would have been class 1, but just because we're dealing with bacteria, that's class 2.
Is there any predicate device that you could use to do a 510K with, or what would be the regulatory pathway?
As far as I know, all these devices for the detection of MRSA are still in research development stages.
There is one that is, I believe, starting to come out into the market that's using a PCR reaction and not NPS analyzing that we're doing. That's a lot.
So I have a question for the class. How many people know what specificity is? Raise your hand.
Specificity?
Yeah, just raise your hand. Hi. So not that, right? So know your audience when you talk about that sort of thing. Kind of give a brief overview when you say false positives and specificity and sensitivity. Make sure these guys.
Yes, that was good advice. I guess I never even thought about that.
Yeah. Any other questions?
Yeah.
Dr. Nasir has a question.
Alright. Why does PCR have so many false positives? You said there's a lot of them.
Not a lot of false positives.
Would you like to take that, or should I?
Yes, there's not a lot of false positives. What could happen is that, because they're looking at the genetic makeup of a cell, and just because you have a gene doesn't mean it's being displayed, because MRSA does change so rapidly, it can easily be...
Change how?
It can change its genetic makeup easily. That's why it's...
It mutates.
It mutates. That's why it's hard to look at PCR because it can mutate. Like, you can have a strain of MESA, and it can easily mutate into MRSA.
During the time you're doing the testing? Like in between the time, the 48 hours?
Well, the testing the PCR is 4 hours, and all it does is look for that gene. And just because you have the gene doesn't mean you have MRSA. It's not displayed necessarily.
You have a higher chance of developing MRSA. It doesn't mean necessarily have it.
So if it mutates so easily, how can you be sure that the antibody that you're going to use that's going to target MRSA is also going to be specific to it, it's going to stay specific?
The PPP2A antibody came out, research came out around 2005, and since then it still is the protein that controls the cell wall of MRSA and not any other cell.
So you're saying that the mutation doesn't have any manifestation on
To the protein.
the cell wall proteins that are expressed, and they won't change as a result of that?
They could possibly change in the future. I guess I don't know how the bacteria
Depending how it mutates against the antibody.
Because your whole sensitivity is based on the specificity of this antibody. That's how it's working, essentially, your channel, your device, how it's working.
Correct, but with MRSA, that is the main issue. as more antibiotics are introduced, it starts mutating and fighting itself against it. So as of right now, this proves to be the best method to pursue with specificity.
So the currently that latex, the other for clinically used test wasn't B2A, B specific.
I guess I'm just trying to get a feel for if, let's assume that this is working exactly like you want to, is it a more sensitive test than PCR?
Yes, definitely, because PCR, they're sensitive as in
Is it
an accurate
more,
measurement.
it's more specific?
It's more specific than it. Sensitive, we have not proven yet.
Yeah, we don't have any quantifiable data, I guess, to prove.
Could you apply the same technique to other disease diagnostics?
Yeah, you'd have to look at different antibody cells because all chemicals interact differently. This is why when we were looking at possibly moving to a different bacteria due to some unseeable circumstances, we weren't able to actually test anything because we weren't able to get any more antibodies because they are so specific. But yeah, you can still use the same, like our device itself, just with different antibodies.
So one of the reasons why your device is so good is because it can do it fast. So why is it that it can work so quick? What are the reasons for it to
So the only other
have a quick
method,
detection time?
yeah, the only other method besides PCR, which takes 4 hours, is a culture, and that you would have to.
Now I'm asking, you're saying your device will work fast.
Right.
Why would it work fast?
And so with culture screenings, you have to amplify your sample. You're growing your sample. With us, you do not have to do that. For our testing, we did a 24-hour culture, so already we're 3 times faster than original method. So what we would do in the future of our device is flow a sample without amplifying it at all, and then we would see a change in impedance and measure that.
So essentially you're using small sample volume.
Yes.
What is your sample volume?
For our flow-through device or our antibody testing that we did earlier.
I mean,
Yeah, I just wanted to double check. Thanks for answering your question. I guess we don't have a definitive number for how much we flow through. Probably.
you have the dimensions of your channel.
Yes.
Yeah.
For report purposes. You should, because the main reason for fast detection is small sample volume. I have a question about impedance. Why is it that the impedance is not scaling linearly? What do you think? You go from 1x to 2x to 5x to 10x, and it's not a linear relationship. What's happening? I mean, I would have thought that if it's just a resistance measurement, it would be linear.
I think the biggest factor is our external sources of error that are contributing. After a certain amount of trials, our devices would unbind, be unbonded. And because of that, we had to take it into account and take all the data we can to get an average.
We did have to switch between some devices in between both of the 10x, 1x.
So it's just external sources of error.
Because we can only push through fluid about 2 or 3 times before the device would start to disintegrate and the bonds would fall.
I guess I'm trying to get to the fact that I want to see, I want you to sort of demonstrate to me that you have a feel for if this device is working exactly, what data would you be getting? What would you see in your data that would tell you that you're getting a detection event?
Currently or in the future when we
Sure,
test
if it's working, let's hypothesize it's working exactly perfect.
Okay,
What
so
would you see from your data?
we would see an increase in impedance when MRSA binds, and through that we have to do a bunch of data analysis to see when we have a specific amount of MRSA, we're getting a specific number of impedance.
But like an increase in impedance where? Like,
on the electrodes.
no, but I mean, at a specific frequency. Because I mean, if you go back to your data, for example, you see your, you showed your conductivity data, and yeah, this one, for example. Why is it that at the 1K, 5K, and 9K, you see that there's a little bit of difference, but then when you go to higher and higher frequencies, it seems like there's no difference between the 3 different concentrations?
We applied the 3 different frequencies. And then when the concentration increases, they don't differentiate much. But at this 1x, they do differentiate.
Yeah, but I'm saying, okay, so there's a frequency at which you see the most difference, right? So you see the most difference.
Well, if we go back to this one, technically speaking, anywhere above, so let's say 20 hertz, all the way to 100, you can pick out any frequency and it will be this peak. But as you get close to 0, you're not really applying a fast enough alternating current.
Okay. I'll buy that. I think just a little bit more information about how it works, because it's not as simple as, you know, a button that lights up red and says, hey, you have this. So there is a little bit of data interpretation. I'm trying to understand what you're going to get you know, from the data, from the units, even if you're doing it with PDF.
Yeah, we'll try to explain that more in the written report. We did try to take a lot of the stuff out during the conversation today, we were getting too specific.
Yeah, another comment on that. I think it would just be nice to see earlier in the report that you know, this thing that we're building has this ability to code these receptors, whatever, and make an impedance change because of this extra layer. I didn't hear that until way late in the talk. So I'm thinking, okay, how does this thing work? Does it work? Does it work? Does it work? And then finally,
Slide 14. You explain on this slide exactly what the principle of operation is.
you know, and you finally said it's because we're going to code this thing. It's going to cause this impedance barrier.
Yeah, how we tried to explain it, we were talking about how we actually set up the device where we put a slide and we slide it in.
So kind of, I mean, just introduce that to sort of a fundamental operating, how the thing works. Just in general.
Like around
Because you
here.
talked about the electrodes, I don't know why I won't even put electrodes up there. Why don't I want to do that? Right? I have no idea. So, you know, it's because of that change. So the principal operating mechanism, I think, needs to work its way a little higher up. That's all.
Thank you. Any other questions?
Thank you.
I'm Danielle Bantley.
I'm Matt Coper. And I'm Steve Freeman.
We're here from the Department of Biomedical Engineering here at Lawrence Technological University. We're here to present our wireless auscultation device for continuous monitoring of heart sounds. Our faculty advisors are Dr. Gerald Carpentier and Dr. Nasir, and our technical advisor is Professor Kenneth Cook.
So for those of you who don't know what auscultation is very simply the act of listening to body sounds in order to make a medical diagnosis. So if you go to see a doctor, you'll normally see that they have a stethoscope around their neck. And this is because auscultation is a very important diagnostic step. So they'll be listening to certain sound characteristics when they auscultate parts of the body. And these parts of the body can be the heart, they can be the lungs, they can also be the intestinal sounds. But they'll be listening to the frequency, which is how high or low pitch the sound is, the duration, so how long you're hearing that sound, as well as the intensity or volume of the sound. This can be very important to determine the structure of that body part. For example, the heart, you could be hearing whooshing or sloshing of the blood within the heart, or in the lungs, you could be hearing crackling or popping noises in the airways. So for our project, we're focusing only on heart sounds, and this is actually, heart sounds are created as the blood flows to the heart valves. When you're doing an auscultation exam of the heart, we put the stethoscope in 4 key areas, so we can look at each of the 4 valves of the heart. The frequency range for the heart ranges anywhere from 20 to 650 at the most extreme ends. And when you hear an abnormal heart sound, this just means that there might be a murmur. Two of the main murmurs of the heart would be regurgitation. This is just a backflow of blood across the heart valves. Or there's stenosis, and this is a thickening of the heart valves, which could make opening and closing of the valves tougher. Matt has a digital healthy heart sound that we're going to play for you. So in this case, if a clinician heard this sound, they would diagnose that this is a healthy heart.
So the current methods of performing auscultation involve using a mechanical stethoscope or an electrical stethoscope. Mechanical stethoscopes' benefits are that they're fairly cheap, ranging anywhere from $15 to $100. They don't require a battery in order to use them, so you can use them anywhere and you don't require power. The downfall is that they acquire poor sound quality and they suffer from outside noise, as well as they're not hands-free. For the electronic stethoscopes, they're able to filter out noise that you don't want to hear, as well as amplify sounds that you do want to hear. But the downfall is that they're fairly expensive, ranging from $250 to $1,000, as well as they require a power source, and they're not hands-free as well. So the motivation for our project, we saw a problem where basically stethoscopes don't monitor heart sounds continuously, as well as they don't do this hands-free. So some useful applications would be things like diagnosing a patient with an infectious disease. For example, if a patient has Ebola, you wouldn't want to keep coming into contact with that person. You want to just stick something on them and be able to monitor their heart sounds. You can do this remotely from the comfort of your office. Also, pharmaceutical interventions. If a patient is in the hospital for an extended time, putting this device on them, you can hear the changes that occur in their body while they're in the hospital bed, as well as being able to monitor more than one patient at once, and then telemedicine, being able to receive the signal or the heart sounds that you receive through our Bluetooth device, and then being able to send that to any physician in the U.S. So we have some project and design goals for our project. First, for the project, we wanted it to be a wireless auscultation device. We wanted to basically where the physician does not need to be present in order to hear the heart sounds. We wanted to make it Bluetooth capable so that it can pair with any device. For our design goals, we wanted it to be untethered, again, so the physician doesn't need to be in contact with the patient in order to hear their heart sounds, as well as low power, which would make the device low cost. And then we wanted it to be user-friendly so that the average medical personnel is able to use the device with ease.
So this is a basic block diagram of the main components of our device. So first we have the microphone, which will pick up the sound. We then have the front end electronics, which is our circuit right here. That is connected to our analog to digital converter, which is the microcontroller. We also have the Bluetooth connected to it, and then the Bluetooth will send data to our computer, and then in MATLAB we'll be able to process our data and store it. So a little bit more about the sound pickup. What we did was we used a simple stethoscope head from a cheap mechanical stethoscope. We cut the tube and we were able to place the microphone into the tube. The reason we did this was without the stethoscope head, we were picking up a lot of outside noise and weren't able to hear heart sounds. With this method, we were able to amplify the heartbeat as well as eliminate some of the outside noise.
So here's a picture of our circuitry, the schematic as well as our actual circuit that we built. The circuit itself can actually be broken down into some building blocks. We have our microphone bias network that we're using to pick up the heart sounds. And we have both a high pass filter and a low pass filter, shown here in blue and red. Then in the yellow block, we have a signal amplification stage. And following that is our last stage, which is a voltage offset. Because we're using two 9-volt batteries, and because our microcontroller operates from 0 to 5 volts, we needed an offset in order to get it in the correct range for what we wanted to use it for. Right here we have the Bode plot. This is just showing the frequency response of our circuit that we created. From this, we could tell that our filters work correctly. We have a high-pass filter at 15 hertz, a low-pass filter at 964 hertz, which creates a total bandwidth of frequencies that we're collecting anywhere from 15 to 964. And also from this, we can calculate our gain, and the gain that we calculated was 75. So after we collect our signal, after it goes through all of our circuitry, we have an analog signal, and now we want it to become digital. So for this stage, we use an analog, Arduino Uno, connected with an SD card shield. So that was an extra component that we stacked on top of our Arduino Uno. And then we developed an Arduino program that sampled our analog voltages at 1,000 points per second. And we chose 1,000 points specifically because we were limited by our hardware. That's about as much as the Arduino can do. So the voltages went into an analog input pin, and this pin, as well as our Arduino programming, helped convert the voltages to bytes. The bytes were stored into a text file on the SD card. So now that the data is stored on the SD card, we want to be able to transfer it. In this stage, we use some MATLAB programming to actually read the data off of the SD card, transmit it through Bluetooth to MATLAB for later data processing. Specifically for this, we use this Bluetooth transceiver known as an HC05. So once we pair that to our laptop, we are able to send data through Bluetooth.
So for data analysis, like Steve mentioned, after the data comes to our laptop, we use MATLAB in order to plot our data, and then we created FFT graphs in order to look at the frequency components. We then use digital filters in order to eliminate any outside noise that we didn't want, such as talking. And then finally, we were able to have an audio of our heartbeat. So for verification of our device, what we did was we used BioPack, which is a data acquisition device. So in port 1, we used the BioPack stethoscope, and we placed it on our chest. And then for port 2, we had a signal cable that was connected into BioPack, and then that connected to our circuit, and then our circuit had the stethoscope connected to it. So we placed both of the stethoscopes onto our chest and looked at our results on MATLAB. So these were our results. The red is our stethoscope and the blue is the BioPack. As you can see, both are fairly similar. You can see the peaks, which is the actual heartbeat, and then everything aligns pretty nicely. So from this data, we concluded that our device our circuit is functional. We then went on to do some more testing. First, we still used BioPack in order to distinguish between healthy and abnormal heart sounds. So what we did was we had a person come in that has heart conditions, and we listened to their heart. As you can see, there are some distinguishable changes. The peaks are larger for the abnormal heart, as well as the frequency response here is much larger. I will play for you now examples. This is a healthy heart. And this is the abnormal heart. As you can see, both are very distinguishable differences, and from that we can conclude that listening to heart sounds, we can detect various problems with the heart. We then went on to compare our BioPack and the Arduino. So what we did was we tested it in a silent environment first. The blue is the BioPack and the red is the Arduino. From the data shown here, it seems like our Arduino picked up more noise because there's more variation in between the peaks. Although when we listened to our results, it didn't really seem so. So here's our BioPack. And then here's the Arduino. And this was done without any filtering, so this was just clean data that we got from our device. So next we tested, same scenario, but we were talking in the background. So right here you can see there's more variation on the graph. There's more like differences, so we were picking up more noise of the talking. So here's an unfiltered example, and as you can hear the talking. This is the BioPack, and then this is our Arduino. Fairly similar. And then next what we did was we used that exact same data, but this time we tried to filter out the talking. So right here you can see on the left, the variation is a bit smaller. Once again, it seemed like there's more variation in the Arduino, but that our results didn't. The sounds were still pretty nice. So here's the BioPack after it's been filtered. And then here's the Arduino. As you can hear, the sounds are a little bit more quiet compared to when it wasn't filtered, but you can hear a heartbeat now instead of the talking. So we concluded that we are able to eliminate some of the outside noises in order to hear a nice heartbeat.
So after looking at the data, we can conclude that we have successfully created a wireless prototype that can collect and send heart sounds via Bluetooth. We've also successfully created a MATLAB program that can process and play back heart sounds. We also conclude that our device can compete with mechanical and electrical stethoscopes. Basically, the ease of use, the sound quality, and the cost, our device competes with those stethoscopes as well. So for future improvements, we'd like to do something that could eliminate more noise, so we want to test out more sound isolating materials. We also want to miniaturize the device as much as possible so that it's more comfortable and fitting for the patient. We want to try out incorporating some adhesive material so that it can stick to the patient without needing the physician to be there again. As well as adding the central monitoring system so that more than one patient can be monitored at one time just by a simple click of a button. And then we want to incorporate other body sounds such as lungs and bowel sounds. So the way we thought about miniaturizing our device is using something called a printed circuit board. That's what you can see in this image here. It's fairly small. That would eliminate the need for our circuitry there. We also thought about using a piezoelectric transducer, which is shown in the middle image, as well as you can see the size here. That will eliminate the need for the stethoscope head as well as our microphone. And then we want to use smaller batteries so that we don't need the 2 9-volt batteries that we're using now. And we also want to use a microcontroller that's miniaturized, similar to that image on the left. That will eliminate the need for the Arduino Uno, which you can see is fairly big, as well as the Bluetooth module.
So, for the division.
Our estimated price for our project is about $50, which again, it competes with both mechanical and electrical stethoscopes.
So for our division of work, Daniel was incorporating the filter coding as well as the group interfacing. Matt worked a lot on the BioPack testing as well as the MATLAB analysis. And I worked on the analog to digital conversion as well as the data transfer. And then as a group, we came together and developed the circuit as well as did the Arduino circuit testing. Here's our timeline. For the most part, a lot of our tasks were broken down into testing parts of our programming at a time or testing parts of our circuit at a time. We began by simply testing with BioPack and testing with a simple Arduino to MATLAB program. Then we kind of stepped that up and we went to adding in Bluetooth to our programming, and then we added in the SD card after that. So we had multiple stages of programming that we went throughout the semester, as well as testing. We went from BioPack to Arduino testing. Some other important tasks to note: we submitted an abstract to BMES, and then we also prepared for our poster session in this final presentation during our time.
So to conclude this presentation, we would like to acknowledge our advisors once again. Our faculty advisor, Dr. Gerald Carpentier, he helped a lot with Arduino programming as well as he provided the Arduino Uno itself. Dr. Nasir helped a lot with MATLAB programming as well as providing various materials. And then Professor Cook, he helped a lot with circuit development as well as testing our actual product. And then he also provided us with a lot of materials and knowledge. And these are our references. And we'd like to open up for questions.
Same question as the other group. What class of medical device is this, and what regulatory pathway would you use to get it?
Class 2. Why?
Because of the electrical components. And then probably like the 5-10K.
So there's a predicate device?
We would use something like the ECG, wireless ECG thing that we found before, similar to that.
Are you interested in pursuing this further and commercializing it?
We haven't talked, we talked a little bit about it and we're still deciding, but we could potentially continue this on into the summer.
Is there any intellectual property? Have you done like any patent searching or anything?
I mean, we did patent searching at the beginning, but we didn't do any patents on our device.
My suggestion is to avoid, don't make it a medical device, make it a qualified self-device, and you could sell it legally. Much easier. I mean, like I have a heart rate monitor that uses the light on my, and the camera on my phone, but there's heart rate monitors built into watches and things. So, do you think there would be a commercial, like people would just want an auscultation device to wear while they're exercising or something?
They could. That was also another thing we were thinking about where patients could just place it on their chest and monitor their heart throughout running. Yeah. Just like people.
That would be probably your minimum viable product if you were to commercialize it.
Okay, I had questions. I just got a little confused in your results, what you were filtering, what you weren't filtering. You showed that the overall design had filter built in. Right, so you could go back to that slide. So this thing, this was set, right? Or did you float out that filter, those filters in the front? When you measured stuff later on, you're comparing things that were filtered and unfiltered. Did you take that low pass and high pass filter?
No, those were built in there, but due to the range that we were collecting, it was more than enough where it didn't interfere with the heart sounds.
No, I think the question
Right, but when you're comparing, right? So if you go to the next plot, the Bodie plot, which I'll talk about in a second. Just for reference, if you're going to put log frequency, put log. Oh, it is log. It's a little odd. But anyway, all right. So it never gets quite flat. Then when you compare that to the biopack, when we say unfiltered biopack, how unfiltered is unfiltered? I was just a little bit lost in terms of.
They're at the plateau, right?
Yeah.
The filter cuts off everything outside of the plateau.
Yes, so are the front-end electronics always part of both setups? With the biopack and without the biopack?
Yes.
Were you always using front-end electronics?
Oh, yes.
Yeah. Oh. See, that was unclear. Okay. I think that's exactly what he's getting to.
All right.
It's unclear. You're just using the biopack in replacement of the Arduino board.
Right. The first test that we did with the normal and abnormal, And that was with BioPack, but everything was going through our circuit. The only time it wasn't was for verification when the BioPack stethoscope went from the BioPack to ours. But everything else went through our circuit.
All right, well, then I have no idea.
But then the analyzing process was either Arduino or BioPack.
Then I don't know what's going on. I mean, how can you explain?
That's
Yeah.
Yeah, I had the same question. Why are you getting so much noise with the Arduino? I don't understand.
Well, I mean, we have a lot of wires that are just sticking out, things like that, so that picks up a lot of noise. And our device to pretty much just prove that it works. We still have a lot of work to do with finding out how to better isolate the sounds and things like that.
So did you use any shielding for your?
No, this is what it is right here.
Oh, so the one that's going through the Arduino port was using these wires,
yes.
And then the one which is through BioPack, that was shielded, right? You're using the one that comes with it.
Well, the BioPack was just a BioPack system, and then we just had a cable going from the BioPack.
The cable that comes, were you using these cables, or were you using the BioPack?
No, the BioPack, the one that you screw into the channel, and then.
So that would explain it.
But still, those are short. Those are small. I don't understand the difference between, unless there's some other filtering that's going on in software that you didn't turn off or not. I mean, maybe go ahead and plug into the results so you can fit it.
This was just a BioPack.
Yeah, so comparing BioPack with the Arduino.
So their noise is all 15 hertz, which is their cutoff, the low pass cutoff.
Yeah, it's a single pole forecast. It wouldn't cut it off.
I mean, it seems like BioPack would be cutting stuff out where you don't.
Yeah, are you sure that BioPack doesn't have a built-in filter?
I think it probably
No, it
does.
does because we actually.
When you set up the channels in BioPack, there are options for high pass, low pass, or notch filters.
And you're sure that you had them turned off?
Yes, we didn't use any of those.
Okay, I just find it weird.
And there's also a spot in BioPack to set the sampling frequency, and there's also 1,000. So.
Sampling frequency.
Do you think 1,000 as your sampling frequency is a good, like if you made a commercial product, is that reasonable?
We'd probably raise it, but especially if you want to do like lung sounds and things like that. But due to the capability of the equipment that we had, 1,000 seemed like it was the peak for what we can process. But what we wanted to do, that was more than enough.
So how much work would it have been to take that same device and use it for long and vowel sounds? Would it just be different?
It would probably be a different microcontroller, right?
Well, lung sounds are a lot higher pitched, so they have a lot more higher frequencies. So we'd have to probably find a different data acquisition system in order to collect the frequencies that we want.
So the lung sounds go up to what?
2,000 hertz.
2K? Yeah.
Have you looked at the literature to see if somebody has used the frequency content of the sound as a way to diagnose conditions, disease states?
Well, pretty much any visit that you see at a doctor or a hospital or anywhere, they will use
Yeah, but
the stethoscope.
Yeah, but they're not measuring frequency. Although you said it, it's a little confusing because when you show frequency data and you say looking at the frequency of beats, you're talking about how many times you have a heartbeat. I'm talking about the actual pitch or the quality of sound. Has that been used to correlate to diagnostic conditions? Like somebody has a murmur, can you look at the frequency content and be able to use that to diagnose? Because if you can, then you've got a new way of doing diagnosis which doesn't rely on a human. Because otherwise, your device always relies on a person to make the call, right? This is still, for a person to make a call, but it's just record it and send over wireless or whatever?
I mean, we did have a specialist record our data and then look at it, and he was able to see what was going on. We don't know how reliable his knowledge was, but from what we believe, he was able to show us, okay, I know what's going on here, I know what's going on here, just by looking at the graph that we had.
I feel like it's important to go back and look at the video for the report to see if that kind of study exists or somebody has taken the frequency content and tried to.
As far as I know, it's easier to look at the actual signal and see if there's like
the time data.
Yeah, the time data, and actually see whether there's like waves for like a third sound, or there might be small waves in between the two peaks. Because that could be systolic murmurs or diastolic murmurs.
Is Bluetooth allowed in medical facilities? Can you send out data over Bluetooth? Is there regulatory restrictions for that? Confidentiality issues?
Well, Bluetooth is actually more secure than Wi-Fi.
Okay, secure is one.
I mean, but it's more secure than Wi-Fi, so.
Because you have to type in an actual code to pair with that one
Yeah,
device.
it's usually 1, 2, 3, 4.
Yeah.
But you can change the code if you don't have to have, that's like the.
I'm asking this because this question was asked to you in your poster session as well. And I think you need to have a good answer for that. It's a clinical device. And if they don't allow Bluetooth connection for medical data transfer, then you need to figure out if you need that's encrypted.
And then the only other thing I was going to say is, I mean, you guys limited yourself towards we talked about just for the class. You know, the lung sounds might even be something because hospitals have a good record of being able to look at different things physiologically and give a little red light on the nurse's station. What's happening? But lung sound is not something that's common. So if you've got like somebody with an aging person who's coming in with pneumonia, it's cleared up. Now, maybe overnight it's starting to. What would you expect to see in that signal that would alert you? What would that concept?
Well, I mean, if a patient was coughing, you'd see a lot more sporadic signal. There'd just be a lot of like high, low coughing.
How about just when you're breathing?
Breathing would be more consistent signal.
Would be what?
There'd be a more consistent signal. Yeah.
What if they're breathing with fluid in their lungs versus not?
I mean, we haven't really looked into detail on lung sounds because we focus solely on heart sounds for our project.
It's just something to look at.
Initially, you said that they listened to 4 different spots, right? So how would you do that with that device? I mean, would you have 4 different monitors, and then how do you distinguish the sounds?
Right. Initially, we would see how our device would pick up data just from one area, but potentially we could, for extreme cases that patients have to have everything monitored around their heart, we could just pretty much create a device where you kind of have the center device and then maybe smaller microphones around it, kind of like a spider-looking device. And that would cover up more of the area and the 4 main spots.
Would you be able to distinguish the sounds? I mean, you were just showing us one sound, so.
Right. That would be something for the future to create a monitoring system for hospitals. That would be something like way further on, but it would be possible.
Yeah, one other point. Can you go back to your early slide? Shout out, John. So the keep going forward. Back. One more. Forward. Well, maybe you don't have it. So, what, I mean, one of the issues you had with the electrical stethoscope was that it was power, right? I mean, and you say it's power. That's a bad thing. But, so you're not going to power it?
No, ours will be powered too.
Okay, so I just want you to kind of maybe downplay that and say, okay, you know, with today's technology, battery technology, do this. That's we're going to do that.
Right. Very good point.
Don't overblow that restraint.
So, thank you. Before you leave, for people in the audience, we also did a poster session if you weren't here 2 weeks ago, I guess. And we had the faculty and also the other faculty from life sciences, as well as industry, people who are part of our advisory board that went around and evaluated all of the students' posters and talked to them. Hey, hold on a second. I'm trying to get it all. So this is the group that won Best Poster. For each of you, as well as a certificate.
It still needs to be signed by
Yeah, so we'll give you the certificate next week. And he's out of town, so we're going to get his signature when he returns on Tuesday. Thank you. Have a good time.